This is Module 12, Lesson 4. You are about halfway through with your lessons for this module. I'm looking through my papers to see how many more you have. I think you have 6. So you're closing in on the end. We do have a practice sheet this time. We have some more formulas to work with. I still don't think that you're going to find that any of this is overly difficult. So let's get started talking about reflection. We need to talk about some properties of waves at this point. So what is reflection? It's when a wave travels into a new medium and some of it comes back to you. You actually could get all of it coming back to you, but at least part of it comes back at you. It's kind of like the bouncing back of light. That's how I think of reflection. How much reflection you get depends on how different the media are from each other. If you've noticed, on some surfaces, you can see your reflection. Obviously, mirrors, you can see your reflection. But you know, like sometimes really shiny countertops, you can see your reflection in. You can see your reflection inside of a car, but that's not a mirror. You can see your reflection in some glass. Glass, incidentally, is how a mirror is made, with like a silver backing behind it. But you know, if you go out and look at pavement, you don't see your reflection at all. Why is that? Because it's basically explained in this little image that I copied off of the internet for you here. You can use my link if you want to get to it. But basically it depends upon the surface. The more irregular the surface is, the more scattered the reflected light will be. If you see your reflection, then you get very nicely, regularly patterned reflected light. So if you held your face over this one and you looked down at it and you wanted to see if you could see your reflection there, you should be able to see your reflection in this one because everything is coming off of it very nicely at the same angles. But if you put your face over this one, your face just got distorted in this one, and so here's your face and you're looking down at this one, you're probably not going to be able to see anything because the light is going off in all different directions, and so you're going to see nothing, which is probably better because your nose grew a little bit and I messed up your face. So, it's okay. All right. So let's talk some details with this. When you have a reflective surface, there are some things that we need to talk about. Okay, light reflected from a flat mirror follows something called the law of reflection. And the law of reflection is this. Remember, this is your Greek symbol for theta, means angle. So the incident angle is equal to the reflected angle. The incident angle is where it comes in at. So in other words, when you see the word incident, that's like your incoming light, and this is like your outgoing light, okay? So here's how this is going to look. Here we have a reflective surface, and then this line right here is the normal. The normal is a line that's perpendicular to the mirror. So you see the red line right here, that's your normal, okay? This angle right here, we are going to label it, since it's incoming, as the theta I, which is the incident angle. What that means is that the incident angle is measured compared to the normal. So if this was 30 degrees, that means this would have to be 60 degrees. So the reflected angle would be this one. It also has to touch the normal. Then this one would be 30 degrees, and this one down here would be 60. Why does it matter so much? Because you may have to draw your pictures on some of these, and I want to make sure that you know not to put the incident angle down here on the reflective surface. It needs to always be touching the normal, okay? So if it comes in at 30, it's going to go out at 30, and you need to know with respect how to draw them. Sometimes, instead of reflecting back at you, light will actually bend. So wave speed depends on the media. So what happens when you travel from one medium into another? Well, then the speed is going to change. The speed is either going to get faster or it's going to get slower. When that happens, you get bending of light. Here's a picture of it right here. So what happens? You just simply have a beaker of water with a pencil in it, and when you look at it from the side, it looks like the pencil is bent, but it's definitely not bent. It just appears to be that way. You may have seen this with a drink that has a straw in it. You may have noticed it with other things, like if you're looking from above and you look down into the water and you see like a penny or something on the bottom of a pool or a pond, a river, whatever, and you reach down to grab for it, but it's not exactly in the place that you thought it was going to be. Instead, it's a little bit over to the side from where you thought it was going to be. That's an example of of the bending of light taking place. It says right here that whenever waves travel perpendicular to the new medium, that they continue in the same direction. So in other words, whenever the waves come in, we're going to have some pictures of this in a minute, whenever they come in and they go exactly perpendicular, they'll continue to go straight. They'll continue to go in the same direction. The problem is that their angle doesn't change, but the velocity changes. And if the velocity changes and frequency stays the same, you know our formula, v is equal to lambda f. If the velocity changes, but this stays the same, then that means your wavelength has to change. And it means that they're going to end up bending, and you're going to see this happen. You're going to see the bending of light. Now, this bending of light is called refraction. So refraction is, you know, the vocabulary word for bending of light. Whenever you have light traveling from a less dense to a more dense medium, it's going to slow down and it's going to bend toward the normal. So here's a picture of this. Let me see if I can show you over here. Forgive the doggy noises. So right here, you have your incident angle, your angle of incidence. We had these before. Remember that the angle of incidence is the angle that you hit going in at. Okay, that is the angle that you are going to, I was going to see if I meant something specific by this. No, nothing different. It's just what I had before. The angle of incidence is, you know, between your ray and the normal. And so we can put that here if you want to. Between the wave, we'll put ray and normal. And then the angle of refraction is also between it'll be between the refracted ray and the normal. So when it comes out, it's going to come out on this side, but instead of heading straight, like if it kept on in its normal pattern, it'd be right here. That's not what it's going to do. If it is going from less dense to more dense, it is going to bend this way. It's going to bend closer to the normal. And then what happens if it goes from more dense to less? I think I paused myself instead of changing colors. If it goes from more dense to less dense, it will end up moving away from the normal. So if this is where it should have gone, then it'll end up moving this way. You know, it'll make a greater angle for speeding up. All right. So what we have that goes with this is something called Snell's Law. It's on page 4 with all of your other formulas. This happens to be on page 1 of your reference table. It is a list of common index of refractions for different substances. Here's Snell's law. It's N1 sine theta 1 equals N2 sine theta 2. What does all of this mean? N stands for the index of refraction, basically of thing 1 and thing 2. And that's all it is. And then you have the sine of the angle of substance 1 and the sine of the angle of substance 2. That all sounds crazy, but it's really simple when we put it into practice. So I have some example problems for us. I'm going to be getting my numbers from this table right here unless otherwise given in the problem. So here's an example. It says a ray of light traveling in air. So we've got it traveling in air. It strikes a block of quartz. So there's our two substances. We have air and we have quartz. And it hits the block of quartz at an angle of 15 degrees. So here's what we need to do. I prefer to kind of draw this out so I can see what's happening. There we go. So we have a block of quartz right here. And I'm going to draw my normal-ish. Close enough. Good enough for me. So we've got the angle coming in, and it hits at an angle of 15 degrees. So that angle has to be touching the normal. So that's our incident angle. It hits at 15 degrees. Find the angle of refraction. So we don't know exactly where, but we know that we are hunting this. We don't know, I may not have drawn it properly. It may have sped up, it may have slowed down. We don't really know, but we're going to figure it out using this. Not Ni, but N1 sine theta 1 equals N2 sine theta 2. So we're going to work on this way. We're going to do, actually, let's change that. We're going to do air on the left and quartz on the right. I could have flipped it. I started to, and then I was like, nah, let's just do what it went into and what it is going through. So the index of refraction is what we need for air. So go back here. For air, it's 1. So it's 1.00 times the sine of 15 degrees. I'm coming up with that because that's our initial angle. That's the angle it went through the air at. And then we have the index of refraction of our second substance, which is quartz. So go back here. Quartz, we're going to assume that it is fused quartz because that's the only quartz that we have, is 1.46 the sine of that theta. That's what we're hunting, is that theta right there. So if you put all of this in your calculator, you will get a theta equal to 10.210 and some change. Now let's talk sig figs. The only thing that's going to apply here with sig figs is this. The indices of refraction, all of those different indices are like their reference table numbers, so we're going to consider them to have an infinite number of sig figs. So they don't matter. So we're limited to 2. So our answer will be 10 decimal degrees. 10 period degrees is what the angle of refraction will be. So what that means, if it moved toward the normal, you can go back to this if you want to. If it moved toward the normal, that means that it slowed down. That's what that's indicating to us, is that it slowed down. Okay? All right. I have another example. A ray of light travels from underwater into air. So there's our water. Here's our normal. It's traveling from underwater. Oh, that's a really bent ray right there. Oh, well, close enough. It travels in the air at an angle of 65 degrees. So here's our incident angle right here. That's still really bad. It's going to bug me. We'll see if we can improve here for the sake of me. There we go. There's our incident angle. And then it travels through the air at 65 degrees. Now, should I draw that 65 degrees on this side, or should I draw the 65 degrees on this side? Remember, it has to be touching the normal, the perpendicular. So it's got to go here, 65 degrees. Find the incident angle. Okay, so we're doing the same thing we did last time. We have n sine theta equals n sine theta. I typically drop the 1s and the 2s because I'm lazy. We've got water versus air. We can set it up that way. Okay, so water. What's the index of refraction for water? Well, here, I'm just going to use my reference table and quit flipping back and forth. For water, it's down at the very bottom, is 1.33 times the sine of some theta. This is the one that we're hunting. We want the incident angle, the one for the water. And then it goes into air. The index of refraction for air was 1 at a sine of 65 degrees. That's all that there is to this. Solve it for theta. And that would be my beagle. My dogs are driving me crazy this morning. I'm sorry. She wants upstairs. Someone will get her in a minute. So we have 42.955. Let's talk sig figs. It's like last time. We only have one number here. Got 2. So since this has 2, we're going to have to round this to 2. So that is going to round to 43 degrees. The 2 is going to go up because of the 9. So we have an angle of incidence of 43 degrees. Okay, I have something else for us to do. We can also determine the index of refraction for any substance. You have this on your reference table as well. It is on page 4, just like all the others. It's the third one down. N is equal to C over V. N is the index of refraction. There is no unit for this, just like we didn't have a unit on the reference table for the index of refraction. It's just a number. Then there's no units. The speed of light. This was on your reference table, remember. It's 3.00 times 10 to the 8 meters per second. And then you have the velocity or speed of the other substance, which, since this is in meters per second, will have to be in meters per second. This was on page 1 of your reference table. You can find it there. So here's an example. What is the speed of light in water? Now, obviously, I'm not using it to find the index of refraction for this particular problem, but I could. Okay, we can also use it to find the speed of light in a different substance. So if it wants the speed of light in water, we're going to use this. The index of refraction of water is 1.33 using the table on the first page of our reference table. The speed of light in a vacuum is what's going to go up here, which is 3 times 10 to the 8th meters per second. And then we can find the speed of light in water instead of air. We solve for V, we are going to get 2.26 times 10 to the 8th meters per second. Now, this is kind of a weird sig fig thing. All of these technically have an infinite number of sig figs because they're all reference table values for what we just did. I mean, nothing was given to us in the problem. So what I would do is round to the same number that was in my reference table values. Like this had 3, this had 3, so I'm just going to round it to the 3. What you can see is that the speed of light is actually slower in water than it is in a vacuum. So, that's what it tells us right there. So we can use this in order to do slightly different things. I think you'll find this fairly simple, so therefore my practice problems, I only gave the one example. It could give you the speed of light in a substance, and then you have it in the vacuum, and you could find the index of refraction of a particular substance. We have a couple more things that go with this. This is our lengthiest lesson. Whenever you have something like fiber optic cables, what can happen is you want to keep a light beam inside of that cable. You don't want any of it to come out whatsoever. So we end up with something called total internal reflection. What I put on the screen says, you know already that you can bend our light. Whenever you have light going from a more dense to a less dense medium, it refracts away from the normal. So if we can bend it far enough down, and we can get it right here, that's called the critical angle. When it travels exactly parallel to the boundary of the medium, or the media, like between the two different media. So this says water, this says air. If you can get this angle right here, it's called the critical angle. If you can adjust the incident angle to where it goes exactly 90 degrees, that is called the critical angle, okay? And then you can also adjust that angle enough that instead of traveling right at the boundary, it actually comes back inside the substance and stays completely inside. That is called total internal reflection. Where we take advantage of this is with fiber optics. We have a lot of companies in our area that do this, like Corning and CommScope, who make fiber optic cables. And what they're doing is they're playing around with either the critical angle or total internal reflection, okay? What we're going to be able to do is we are going to be able to find this. We can find the critical angle. And like I just said, the critical angle is the angle where the angle of incidence equals, that should be an angle of reflection of 90 degrees, not and. Okay, so where we get the critical angle to where it goes directly with the medium. And as you can see, this does make a critical angle of 90 degrees. It makes it perpendicular to the normal. Okay. Total internal reflection, what I just said, is where the incident angle is greater than the angle of refraction, and all of the reflected ray goes back into the medium, okay? We have a formula for this, and I don't know why I didn't label these for you on here, but that's okay, we'll just do them together. Theta C is the critical angle. We have a formula to find the critical angle. And then your ends are the index of refraction of said substances. So for both of those, you have substance 1 and substance 2. So if we use the indices of refraction, we can figure out what will make a critical angle of 90 degrees, basically. I mean, that's all we have to do is figure out how we're going to come up with that. So here's an example. Find the critical angle for light traveling from water into air. And I think I only have one example of this too. Okay, I said draw a diagram. So here we have water. Here we have air. Here's our normal. So we want to figure out what would be the critical angle for making it travel right here. We want this to be 90 degrees. That's what we're going for, okay? And so what we're looking to do is the sine theta c is equal to N2 over N1. Probably the most common thing that people would do is flip-flop these, which is going to totally change our answer. What we are looking to do is to put our two indices of refraction in here. The substance that you're in first is going to be N1. So water will be N1 and air will be N2. So that means air is going on top. Air is 1 and water is 1.33. I'm getting these off of page 1 of the reference table where we've been getting our N values. And we need to solve for the sine of theta. If you do that, your theta is going to be 48.9 degrees. Now, again, I don't have any numbers in this particular problem, which means I'm just going to round it based on the numbers that I'm pulling off of the reference table. These have 3, so I'm going to go with 3. That's just the easiest way to do it when you have nothing given to you. So in this particular example, the critical angle that would make it travel perpendicular to the normal would be 48.9 degrees. We would need, if we had like a flashlight here, and we're aiming this flashlight at the top. So here's our underwater flashlight. We've got the beam of light coming up this way, and we are shining it at the surface of the water. We would need to aim it at 48.9 degrees in order to have it all travel right down the surface of the water. It would be kind of cool. It wouldn't come out at all, okay? And if we made that angle even larger, if we came up this way, we should see it come back in with total internal reflection then. So if we went greater than 48.9, that's what we would end up getting out of that, okay? So before I finish, there is one more formula that is on your reference table that honestly I have done nothing with, and it's this one. It's in, I think I did it backwards. I did. Well, I did write it backwards. It's N1V1 equals N2V2. We can flip-flop those two sides around. One of the other things that you could do, if asked, is you can relate the index of refraction and the speed of something together. You know, it should be something that's easy for you to use. It's just another variation of basically the 4 formulas that we've done in this particular lesson, because we've had this, we've got finding the index of refraction. We've got this one right here. There's 1, 2, and then we had this one, the n sine theta equals n sine theta. So we have all 4 of these that you could use. If you happen to need to compare speeds and indices of refraction, you could use this formula that's on your reference table too. I think chances are anytime I've ever done this, I've probably used some combination of the others rather than pull out the 4th formula, but you do have it if you need it. So now it's time to practice. I have practice problems for you where you can try out the different formulas. You let me know if you need any help. I'll be available if you need me.